Okay, so in the actual section, we solved for the even bound states. Now we're going to be asked to, for problem 2.29, to analyze the odd bound states for the wave function of the finite square well. And then after that, we want to derive the resulting transcendental equation in the exact same way for the allowed energies, and then we want to solve it via Desmos graphically, and after that, examine the two limiting case scenarios. And then our final question is whether or not there's always a bound state. So before we get into everything down here, let's just take this one step at a time. Previously, we assumed that the resulting wave function was even. So the problem with defining, or not a problem, but so we defined the wave function as even, which resulted in the following setup. F e to the negative kx and d cosine lx, and then psi of negative x at x greater than a, x is between 0 and a, and then x is less than 0. So if we want to go down to the odd state and get the second half of the valid solutions, all we have to do is replace the d cosine lx with the other term in the more general system setup, which is c sine lx. So we replace d cosine with c sine, because sine is an odd function. So if we want to analyze odd wave functions, we replace d cosine lx with c sine lx. And from that point, the method for solving this is the exact same as before, where we just take the same continuity conditions. So continuity of psi and d psi by dx at x equals a. Let's start with continuity of psi. We have f e to the negative ka has to be equal to c times sine of la. And then the continuity of the derivative at x equals a, this is going to give us negative k f times e to the negative ka has to equal L times c cosine of LA. And at this point, to get the transcendental, we do the exact same thing as we did before, where we divide the bottom one by the top one. This is going to give us negative k, negative k, and then the f e to negative k cancels. And then over here we have the c's cancel, so L cosine LA over sine of LA. Condensing this gives us negative k equals L cotangent of LA. And next, we're going to do the same variable setup to change this into an expression in terms of z. So as before, we define z to equal LA, and we define z naught to equal a over h bar times square root of 2m v naught. And if we do this, then what we can do is we can say that k times a is actually equal to the square root of z naught squared minus z squared. And at this point, if we replace everything, what we're going to get is negative k is equal to, L becomes z over a times cotangent of z. Move the a over to this side, we have negative square root z naught squared minus z squared is equal to z cotangent z. Move the z over to the other side, we get that cotangent of z is equal to the negative of the square root, move the z into the square root, and we get z naught over z squared subtracted by 1. So from this point, we have effectively finished the problem. All we really have to do now is we have to plug this into Desmos, and if you do, what you'll find is that the resulting graph of valid solutions looks kind of like an inversion of the even functions. Because if we remember, the even functions had this exact same sort of setup, but it was sort of mirrored and on the positive quadrant instead of on the negative side. And at this point, we just have to look at the corresponding limits. So our two limits are 1, when z naught goes to infinity, and 2, when z naught goes to 0. So in the z naught goes to infinity case, we have z naught goes to infinity. Our expression is cotangent z equals negative square root z naught over z squared minus 1. If z naught goes to infinity, this entire thing is infinity. So then what we have is that cotangent of z equals negative infinity. And hopefully you still remember your trig, because this has a very fairly obvious solution. It is z is equal to n pi over 2, where n this time is even instead of odd. So n is equal to, 0, 2, 4, 6, blah, 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 blah. So this gives us the opposing counterpart, because in the z naught goes to infinity case for the odd solutions, we had z equals n pi over 2 as well, but n equals 1, 3, 5, 7, and so on, and all the other odd terms. So this gives us, effectively, the second half of the valid solutions for our infinite well. Alternatively, in the z equals 0 case, here, we have the same problem as before, where this is going to give us an imaginary, which doesn't really make any sense. Instead, what we have to do is we have to go on Desmos and graph this function and then look at what happens as we make z naught smaller and smaller. And we'll see sort of the same behavior as before, where the number of solutions gets smaller because this green line sort of starts to get more and more stunted. I think near the end, it starts looking something like, it'll look like this for a smaller z, it'll look like this for an even smaller z. Now, the key point is that in the even case, there was always a valid solution, no matter how small z naught got, up until the point where it got to 0. In the case where it equaled 0, there was no longer any valid solution. But right before that, there was always going to be at least one valid solution, no matter how weak z naught actually was. It turns out that this isn't necessarily the case for the odd set. So if we graph the extreme case where z naught just gets smaller and smaller on Desmos, what we'll see is that there's a cutoff point after which point there's no longer any valid solution for the odd systems. And this sort of makes sense because what we're expecting is that there should only be one valid solution. So if there's only one valid solution, it doesn't make sense to have a higher one because, once again, these solutions correspond to energy states. So if you have a very weak well, realistically, there should only be one bound solution anyway. It doesn't make sense because if your well is super weak, then jumping up, even by a little bit, is going to cause the resulting sort of energy to become greater than the actual depth of the well, and then you start dealing with scattering states instead. So this is something that we sort of expect, effectively. And with that, we have solved the odd component of these solutions, and we are done with 2.29.